Good morning and good afternoon, good evening. Welcome to the second of a three-series tableting webinar hosted by Natoli Scientific. We are excited to share with you our tablet development technologies, including direct compression, dry granulation, wet granulation, and the tableting process. My name is Carrie Cruz, and I am an office manager and lab technician for Natoli Scientific in Telford, Pennsylvania, and I will be moderating these webinar series. Before we get started, I would like to go over a few housekeeping tips. Our presenters will be sharing their slides, and if you would like to see all presenters, please select all in the drop-down menu. Also, you will be muted during the webinar, so please write your comments and questions in the chat box and I will address them. Also, at the end of the presentation, there is a QR code that you can easily scan with your camera to provide feedback to the presenters. And finally, any questions we do not get to by the end of the webinar, we will reach out to you directly. So with that out of the way, I would like to hand this over to Robert Sedlock, the director of Natoli Scientific. He is a leading expert in the tablet compression industry with over 20 years of experience and has authored numerous technical papers for pharmaceutical technology, American Association of Pharmaceutical Scientists, and peer-reviewed journals. Mr. Sedlock is responsible for solid dosage, customer support, training seminars, contract compression services, and continuous research in collaboration with many universities worldwide. Robert?
Yes, thank you, Carrie. Good morning, good afternoon, good evening to everyone. We appreciate you logging in and signing up for our three-series webinar. This is our second, like Carrie said. We did our first one on compaction emulation and granule tools with powder characterization and micromeritics. So to give you a background of Natoli, I work for Natoli Scientific in Telford, PA. We're a division of Natoli Engineering Company in St. Charles, Missouri. Natoli Engineering was founded in 1973 by the late Carmelo Natoli, now being led by our president and CEO, Dale Natoli. Natoli's facility in St. Charles is over 120,000 square foot. It's a campus that includes compression tool manufacturing, tablet press manufacturing, from single station to benchtop R&D equipment up into manufacturing scale rotary tablet presses, all within Natoli's AIM data acquisition system. We offer spare parts for all industry tablet presses, not just Natoli, but all the common industry machines out in the industry. We offer spare parts and accessories. We also have encapsulation parts and accessories as well. The industries that we serve here at Natoli Engineering Company are pharmaceutical, nutraceutical, food, confectionery, the cannabis industry, and industrial applications. Natoli has many off-site service centers, including Long Island, New York, Cypress, California, Poland, and we work with many universities worldwide on combating tableting defects. Another center that I work at is called Natoli Scientific, and we're in Telford, Pennsylvania. We've got over 14,000 square feet of facility here for R&D, scale up, contract services, and a training center. The facility is equipped with a full line of tableting, from compaction emulation to single station tablet presses to R&D rotary to scale up into production. We also have high shear granulation, roller compaction, dry granulation, film coating equipment, and we have a lot of focus on micromeritics. So we help our customers understand any issues you might have in tableting and manufacturing scale, or even R&D. We look at things like particle size distribution, moisture content, the morphology. So all this equipment we look at to evaluate your tableting issues you might have from R&D into production. And one thing that we focus on is the scalability. There seems to be a disconnect from R&D to manufacturing. So we try to fill that gap, so we provide data that goes into the manufacturing scale. So with that being said, I'm going to hand it back over to Carrie.
Thank you, Robert. For this second webinar, we were fortunate enough to work with Alexanderwerk and Al Friedrich. Alexanderwerk was established in Germany over 130 years ago. They have focused exclusively on manufacturing dry granulation technology for over 75 years. Al Friedrich is the national sales manager for Alexanderwerk Incorporated. His background has been extensively in the powder processing industry, focusing on blending, drying, milling, separation, CIP/SIP systems, and dry granulation technology. Al has a mechanical engineering degree and an MBA from Rutgers. At Alexanderwerk, his focus is on sales and development work in the technical center for pharmaceutical and fine chemical industries. Now to quickly review our agenda for today. During today's discussion, Al will present an overview of the theories of roller compaction, how the equipment is configured, and how the systems are controlled. He will then go into the specifics of processing the 3 blends of APAP material along with the granulation results. Finally, he will tie this all together by analyzing the tableting results on the Natoli press along with the tablet performance. After Al, Robert will discuss the details of the rotary tablet press and the tabletability profiles from the 3 APAP blends. Without further delay, I will let Al take over from here.
Good morning, everyone. Thank you for having me here at Natoli Engineering today. And what I'd like to talk to you a little bit about is the study that we did in conjunction with Natoli Engineering about roller compaction of an APAP material. So before we get to that, let me give you a little background on Alexanderwerk, who we are, where we come from, what we're doing, and then get into the details of the equipment that was used for this particular study, and then how we actually ran this particular study and the variables that we looked at. So just to give you a quick background, Alexanderwerk was founded a long time ago, about 130 years ago. We specifically focus today on selling roller compaction equipment throughout the entire world, focused on pharmaceutical and the fine chemical and the life science and nuclear industry. We cover literally the entire world. Our headquarters are in Remscheid, Germany, and American operation about a half an hour north of Philadelphia. So what were we doing? We were looking at trying to take a powder material, which was very, very fine in form, and we're going to convert that into a free-flowing granule. I'll talk a little bit about why we're doing that, and there are many reasons we're going to be doing that also. So we're taking a powder, and just through compression, we're compressing that powder into flakes. Those flakes then are going to be gently milled up into what's known as granules, and then the granules go on to one of Robert's tablet presses, and we make tablets from those granules. One of the key reasons for making granules is to enhance the flowability. Some of you may know or may not know, tablet presses run at a very, very high speed. They can run in excess of 250,000 tablets per hour. So the material must flow into the tablet presses uniformly and smoothly. So one of the main reasons we're going to be preparing granules are to avoid segregation. You have to have a very, very homogeneous mixture of material going into the tablet press, otherwise you'll have an underdose or an overdose of the material coming out of the tablet press. So we want to make sure that the powder doesn't segregate as we're going into the next process step. And a couple other reasons that we may prepare granules is to produce uniform mixtures, as I talked about, also to enhance the flow of the powder, and also to make a dust-free formulation. Today, you hear quite often in the industry that OEB or OEL levels are always a concern, and dust is always going to be a problem. You have to address that. The more dust you have, the larger concerns for OEB or OE4 exposure risk. Some other reasons is we may want to produce a final granule that's in a certain particle size distribution range from X to Y. We also may want to use some recirculate some unused fractions of a material, and sometimes we have to roller compact material or dry granulate to alter the bulk density of the material. This can get into a long discussion, but basically what you're trying to do is target having all the material going into your final blend being a similar bulk density and similar size so you can avoid segregation concerns. So how do you prepare granules? There are 3 different methods, and Rob and I looked at a couple different methods, and what we're going to be discussing in the next 20 minutes is how you do it using dry granulation. Sometimes you can just do a direct compression, which is easy and quick. Doesn't always work. And then you may opt for a more intense method, which would be dry granulation. And then also we'll be looking at wet granulation, which is the most involved method. So today let's talk about dry granulation using the roller compaction technology. So dry granulation using a roller compactor, it's actually a continuous process. Alexanderwerk has quite a few machines that run on a 24/7 basis, mostly in the fine chemical industry, but could be done in the pharma industry also. So it's a continuous process. It's very reproducible also. When you run a roller compaction process, providing you have the same input parameters and the same machine parameters, it's going to be a very reproducible outcome. Interestingly enough, doing roller compaction, you don't need any additional binders or any water or any other types of binders that may be available. It's simply a system or a technology that uses the van der Waals forces between the molecules to compress those molecules together and hold them together into a solid flake, which we then grind up into a smaller granule. Another major benefit is there's no additional thermal processing required. So if you have very heat-sensitive APIs or volatiles in there, there is no thermal concern about the material being processed. A lot of customers ask, what kind of a delta T do I see across the system as I'm running a roller compaction process? And typically it's limited to about 3, 5, 10 degrees Celsius, maybe from beginning to end. It's a very low energy consumption, obviously, since we're not putting a lot of heat into the product. We don't need to spend a lot of energy to do this operation. Low investment costs when you look at versus wet granulation, and it's a very small space or footprint that's required to have this technology on board. So what's actually happening in roller compaction? Here's where it gets interesting. What we're doing in a roller compactor is we're taking two counter-rotating rolls and we're presenting material to these two counter-rotating rolls. We present the material and it enters these two counter-rotating rolls in an area that's at first called the slip region and then the nip region. So in the slip region, the particles are rearranging themselves, basically finding a space that they can fit into. And then in the nip region, the particles have no more mobility. They're simply being compressed. They get compressed to the point of where the two counter-rotating rolls are at their smallest point, and that's going to also determine the thickness of the flake coming out of the machine. Interesting view here. If you take a look at one of the machines that we have, it's a WP120 that's pictured here. You can see the pictorial diagram that I had on the left-hand side. And on the right-hand side, you can see an actual cutaway view of the machine. What we've done is we've removed one of the side seals of the machine. So you can see in the middle there, there's the outlet of the feed system. The powder, as you can see, is getting compressed, and you can see directly there is a very definitive line of where the powder has actually started to compress into the flake form. And that's where that region is, which transfers from the slip region into the nip region. We'll talk more about that in the upcoming slides also. The Alexanderwerk machines actually have vertically aligned rolls and a horizontal feed screw. There are some distinct advantages to this technology because we use our feed screw more as a metering screw. We're actually removing the effects of gravity. So when you're processing a large batch, and in the beginning, if you're feeding with an IBC, for example, you may have, say, 3 or 4 or 5 feet of head height of material over your feed screw. By using a horizontal feed screw, it takes away the effect of gravity. So we don't want to see a higher pre-compression at the beginning of the batch versus the end. So for that reason, our technology using the horizontal feed screw is very favorable. The two counter-rotating rolls are interesting to talk about also. They give you a specific advantage when it comes to separation of side seal leakages. Although it's typically minimized on the Alexanderwerk design, if you do have any material that leaks out between the vertically oriented roll assemblies, you can take that material and divert it away from the rest of the process and recycle it back instead of running it through the granulation mills. Let's take a little bit closer look at the granulation aspect of the Alexanderwerk machines. We talked about the compaction, which happens between the two counter-rotating rolls, and the key to granulation actually is to take those flakes and mill them into a granule. I actually find the milling aspect of it a little bit more challenging sometimes than the compression aspect. And the way Alexanderwerk handles this is we have actually a multi-stage granulation system. So the material will exit out from the counter-rotating rolls in what we call flakes. Those flakes are gently milled up at first by what's known as a flake crusher. It's basically a rotating set of knives or rotating set of fingers that rotate very slowly, about 50 RPM roughly. And once those flakes exit the flake crusher area, it falls into a two-stage size reduction or granulation step. We call these the RFGs, or the rotary fine granulators. And the way they work is the first granulator that the material sees will have a screen in that's going to be roughly, say, 3 or 3.15 millimeters. So that does your size reduction from the half-inch flakes that have been generated down to about 3 millimeters. The lower screen in the bottom RFG will control the top size of your material. And typically that might be about 1 or 1.2 or 1.5 millimeters. Depends on the process that we're actually running. So by using this multi-step size reduction concept, we generate the minimal amount of fines possible. Let's look at a side view cutaway of the actual roller compactor again. You can see that the roller compactor has the horizontal feed screw as I talked about, but if you look at the feed hopper, it's an interesting design. It's actually called the combi vent feeder, a combination vent and feeding system. So as the material travels down through the feed screw and gets presented to the rolls, the air has to go somewhere. Remember, we're compressing the material, compacting the material, we're removing air from the material. And interestingly enough, with this particular design, the air actually travels back through the center of the feed screw and then exits out the back section of the combi vent feeder. It's an interesting phenomenon to watch, and it works very, very well. It's actually a patented design from Alexanderwerk. In order to also enhance removal of the air from the product, we use vacuum at the end of the feed screw. The vacuum has a twofold benefit for the material. One benefit is obviously to aid in the deaeration, but the bigger benefit actually is to take the material and pull it out against the side of the feed screw housing. By doing that, the feed screw actually acts more as a metering screw. So instead of the material actually spinning with the feed screw, it's stuck to the outside of the feed screw housing, and as the feed screw passes by each single revolution, it grabs that material and then transports it right to the counter-rotating rolls. So using this technology, we have a very, very accurate transport system to the counter-rotating roll assemblies, giving you a very, very uniform product. Let's take a little bit closer look at the vacuum deaeration system. This is actually a side view from a system that has a dual feed screw setup. You can see the vacuum ports or the vacuum housing right before the roll assembly on the far side of it. It's typically a sintered metal element of very, very fine porosity. That way we're not pulling any product through it into the vacuum filter. And what are we actually trying to achieve? The goal for having a good feed system or metering system to the roller compactor is to produce a very uniform flake. And if you look at the two pictorial diagrams I have here, they're actually NIR analysis. If you look at the one on the left, you can see the sides of the flake for this particular design were kind of weak. The red that you see in the center there is what we're looking for. And when we run the vacuum and have the system optimized, you get a very uniform flake density like you see on the right-hand side here. So what are we actually doing in roller compaction? So dry granulation using a roller compactor really is changing the bulk density of the material. And we're going to look at this a little bit closer, and let's get into the theory of it now by defining alpha. Let's call alpha the compaction or the densification, and that's going to actually be the volume in divided by the volume out. So the volume of the material fed into the machine divided by the volume out of the machine. So if you want to start looking at this in terms of all kinds of mathematics, we can throw in a couple of geometrical designs and speed designs. And basically what it comes out to be, I'm simplifying this in the interest of time today, is that alpha is a function of the feed screw speed divided by the roll speed times a funky constant. And that's assuming the gap is held constant. So if you want to increase the density more while the system is running, you could increase the feed screw speed or decrease the roll speed. If you want to decrease the density, you could actually decrease the feed screw speed or increase the roll speed. You're always trying to work on that particular constant known as alpha and change that from one level to another. So also theoretically, if you want to double your throughput, you could double the feed screw speed and double the roll speed. This is really oversimplified, and we can spend a whole day talking about this if we want to. But for all practical purposes, I'll run through a couple more scenarios here, and you'll get the idea of how the machines actually work. So let's assume we're trying to control our process, and we want to also keep the roll speed constant for this example. We're going to hold our roll speed constant, hold our hydraulic force constant, and keep the vacuum constant. If I increase the feed screw speed, that means I'm pushing a larger volume of material into the roller compactor. What's going to happen then? The gap will increase. That's our resultant factor that happens. And what actually happens at that point is, since the gap increases, but the hydraulic force is constant, my alpha, my compaction force, is still maintained. Remember, on the Alexanderwerk roller compactors, the top roll typically floats and the bottom roll is fixed. Let's take a look at another example. And this is again process control. Let's assume the roll speed is held constant, the feed screw is constant, but the vacuum is also constant, and I increase the hydraulic press force. Just like on Rob's tablet presses, if I increase the press force, I'm densifying the material more. I'm squeezing it harder. So what actually happens is the gap decreases. Another example, if we hold our roll speed constant and our press force constant and our vacuum constant, and I tell the machine I want the gap to increase, what's the resulting factor? That the volume out is actually going to increase. But in order to maintain alpha, the feed screw speed also has to increase to compensate. Last one, let's assume roll speed, press force, and gap is constant, but I increase my vacuum. What actually happens when I increase my vacuum is the feed screw doesn't have to work as hard. So the feed screw speed is going to decrease somewhat. That gives me actually a better control of the process, which is why Alexanderwerk machines typically run vacuum at relatively high levels, 0.7, 0.8 bar negative. What other adjustable parameters do you have in the Alexanderwerk machines? Obviously, there's screw speeds, which are adjustable, vacuums, which is adjustable, roll speed, which really dictates the throughput of the machine, the compacting force between 2 and 20 kilonewtons per centimeter, and then the roll gap is also adjustable. Different roll surfaces are available. We can also look at different side seal technologies that are available, and the granulator speeds and the granulator screens can be changed in addition. Here will be a typical setup of a roller compaction system. You can see you have a feed system introducing material into the feed hopper. The feed hopper transports the material to the counter-rotating rolls. The material is size reduced by the RFGs. And then sometimes there's a screening deck also, which screens out any of the fines if that's necessary for part of your process. Those fines can be recirculated and put back up into the feed hopper so we can produce those granules between a certain particle size distribution that you're looking for. All right, enough about the technology. Let's take a look actually at what we did during this particular study with Natoli Engineering. We were given 3 different drug loads of acetaminophen or APAP material. One was a 20% drug load, the next one was a 40, and the third one was a 60% drug load. All of them were blended with a ProSolve 90 and a 0.5% mag stearate for lubrication. We took a look at the angle of repose of each one of these particular blends. And it was interesting to see the higher the loading of the APAP material, the poorer the material flowed, which really wasn't too surprising actually, because the APAP material is very, very fine and doesn't have flow qualities that are good at all in the beginning. So at a smaller drug loading of 20%, we had approximately a 30-degree angle of repose in the material. At a higher drug loading of about 40%, the material still flowed. It was marginal. It was about a 40-degree angle of repose. But when you got to the 60% APAP drug loading, the material really didn't want to flow whatsoever. It was a poor flow and it was about 50 degrees. The material was put into the WP120 from Alexanderwerk, and the way the machine was configured is we used a 38mm diameter feed screw. We used 120mm diameter rolls, which is what the WP120 actually stands for, and the rolls were 40mm in width. Vacuum that we ran was about 0.74 bar negative. We used our flake crusher running at about 50 RPM, and then the 2 RFGs below. The first RFG had a screen of 3.15 millimeters. We ran it at 50 RPM, and the final RFG had a screen of 1.25 millimeters running at 70 RPM. Our parameters that we ran the system at, in order to be consistent across all 3 tests, was we used a hydraulic pressure of about 45 bar, roll speed of 5 RPM, and our gap setting was 1.4 millimeters. As you can see, the feed screw speed had to increase accordingly from this lower drug loading to the higher drug loading. Feed screw speed at the 20% APAP loading was around 25 RPM. At the 40% APAP loading, we were at 29 RPM, and the 60% APAP loading was around 35 RPM. These are the average speeds that the machine ran at. We just told the machine we want a 1.4 millimeter gap. We set the roll speed, and the feed screw was modulated accordingly by the PLC system that controls the roller compactor. Taking a look at the results, if you look at the feed material, which is on the left-hand side of the screen, you can see it really looked like a very, very poor flowing product. I believe this was the 40% APAP I took a picture of here. Material did not want to flow. The flakes that we generated, and this is the sample coming out after the flake crusher, was a typical flake that you see. Each one of them was about 1.4 millimeters thick. And after the material ran through the RFGs, we were able to produce nice flowing granules that you see on the right-hand side. Let's take a look at some of the observations of the material that we saw in the end. The material did compact very well. It was a good blend. It ran smoothly. There was no sticking to the rolls. The pressure was kept the same to minimize the variables from one drug loading to another. And you can see the bulk density did increase. If we look at the 20% APAP loading, our bulk density increased from about 0.43 to 0.66. Keeping the same parameters as I indicated, the 40% APAP drug loading took a bulk density from 0.4 to about 0.61 grams per cc. And for the highest drug loading, we went from 0.38 to 0.58. And interesting, if you look at all of these bulk density analysis, it gives you an alpha, as we talked about, of approximately 1.5, 1.52 for all the runs. Also interesting to note, the PSD appeared to get a little coarser as we had an increased drug loading. Not uncommon. But the bottom line is the flow after granulation was good for all the loadings. The rest of the study, I'm going to turn back over to Rob and let him describe the findings that he had in his tablet.
Thank you, Al, for an excellent overview of the dry granulation process. Robert will now present the details of the rotary tablet press and tabletability profiles of the 3 APAP blends. Robert?
All right, great. Can you guys see my screen?
Yep.
Very good. All right, thank you, Al, for a nice presentation on roller compaction dry granulation. What I'm going to talk about here is now taking the material that was roller compacted, take it to the tablet press. And this is a 3-series event. We're on our second. The first series, we evaluated something called the presser, which is the compaction emulator. This compaction emulator is a single station press. Here's an image on the bottom. The punches are installed in carriages and they travel through a linear track going through a dosing cam, pre-compression, main compression, ejection, and takeoff, and it's got instrumentation to measure the punch displacement and force. So the advantage of this presser was to run it at 1 meter per second, which is equivalent to most manufacturing speeds. This machine goes up to 2 meters per second, but we ran this at 1. At this part of the event, I'm going to talk about the RD30. We then took that material and we ran the RD30 and we did tabletability studies and we did strain rate sensitivity studies. These are very important studies that we want to perform at R&D stage to we want to find out the failure points of our material. Too low of a pressure, too high of a pressure. What happens? We see capping, lamination issues, disintegration, dissolution issues. We see sticking issues. Then we want to run a strain rate study where we start at slow speed, increase our speed to maximum speed, hopefully covering our full range of dwell time that'll run on production. The RD30 was actually designed for scale up, so it does reach over 1 meter per second at the top speed. So the advantage of the emulator, we've already talked about this in our first series, but you can use less material and get more data. But we eventually need to go to the rotary press system, R&D, pilot scale, and into manufacturing. So the RD30 is our workhorse for doing all of this compaction study, scalability into manufacturing. Like Al said, we basically have APAP formulation, acetaminophen, 20, 40, 60%. We evaluate direct compression, roller compaction, and wet granulation. Our focus here is to compare the roller compaction blends 20, 40, 60 compared to direct compression. If you're not familiar with these 3 processes, direct compression is the least expensive, where you take all our materials, sieve them, and blend them properly to create a homogeneous blend and then tablet. If you don't have good flow properties, compactability properties, then you granulate. So roller compaction is the next logical step after direct compression. So I went over this in my the first event we had, but I think it's important to go through this again because we're going to focus on the rotary press process. This here is an image of the rotary press process, starting with the upper punches are installed, your lower punches installed, and then here's your die table with all of the dies. The first step in this rotary press process is the die filling. So you fill your granulation material in a hopper and it goes into a feed system. There are 2 major types of feed systems. There's gravity feeders and there's paddle feeders or force feeders. You'll notice here, here's our feeder and it says granulation on it. The fill cam is a lower cam that's going to start this process. And what the fill cam does is going to pull that lower punch down and create a partial vacuum with that tight clearance between the lower tip and the die cavity. So when it pulls down, it creates a vacuum and hopefully there's material above it, so it sucks in material. And you'll notice in this image, as the fill cam pulls the lower punch down, there's granulation going into the die cavity. There are a lot of older machines out there and even newer machines that are designed like the old model where the fill cam is pulling down before it gets to the opening of the feeder. So what it's doing is it's pulling in air. And now you're pulling in air. Now the die and the lower punch come underneath the feeder and hopefully your product flows well enough that it goes into the die. where if your fill cam is positioned properly underneath the feeder, it will pull down and suck powder in with that partial vacuum. If you do have a machine out there that has this design where you're not pulling in powder at the fill cam, Natoli has a solution for you. It's called a fast track. So we'll basically custom design your fill cam for your press so it does pull down underneath the feeder. So this might be a common reason why you're having weight variations at high speed on your tablet presses, because this fill cam needs to be positioned underneath the feeder. After the fill cam, you've got your dosing cam or volume adjustment. So it's a two-step process to fill that die. You overfill the die, and then the weight cam or dosing cam pushes the lower punch up and scrapes off the excess powder. So we overfill, and then we push out excess to achieve that weight. So as we're pushing out the excess powder, the powder particles are consolidating, and it's kind of tamping the air out and getting the particles closer together. That's going to give you a more consistent die fill. So you want to overfill your die and push out a small amount, but you don't want to push out too much. You want your fill cam to be about 2 to 4 millimeters more than your dosing cam. So your overfill is only about 2 to 4 millimeters. There are some products that might have some flowability issues that you've already gone into manufacturing. And if that 2 to 4 millimeter overfill doesn't get your weight, then you can increase it maybe to 6 millimeter. But as a formulator and a scientist, you want to make sure your bulk density and flowability is passable before it goes up into manufacturing. So your fill cam should be 2 to 4 millimeters more. So after the dosing, you've got two compression stages. You got a pre-compression, and then you got a main compression. The pre-compression is a deaeration stage. You're consolidating the particles, getting the particles real close together, because then when we hit it with main compression, when these particles are touching each other, it's going to favor high compaction or high robustness. So pre-compression can help you increase the tablet strength. It can get rid of capping problems and some other compression issues. But as a formulator, you want to formulate your product such that you don't need pre-compression. So you formulate fix any capping robustness issues without using pre-compression. Because now when you scale that into a high-speed manufacturing press and the turrets rotating at very high velocities and low dwell times, if you have these issues in tablet compression, you can use pre-compression as a backup tool. But if you develop a pre-compression, you're going to need it in manufacturing, and if you have these issues, you don't have a backup tool. So a good formulator is going to develop it such that they don't need pre-compression at the R&D stage. Now, another thing that's important to talk about pre-compression is I see a lot of companies using too much pre. If you put too much pre-compression force on, you're going to pass the yield pressure of the particles. They're going to fracture and bond. Now you got bonding. You do not want bonding to occur at the pre-compression stage, because when you hit it again under main compression, you're going to destroy the microstructure of those particle bonding. So pre-compression just tamps the air out and consolidates. So from our first series training, we did Heckle plots. And the Heckle plot will tell you how much pressure is required to cause that deformation and bonding. So your pre-compression should be below that Heckle constant. So if you remember the series 1, or you can get the video, we talked about how to generate Heckle plots and understand the yield pressure of your material. Your pre-compression should be below that value. Okay. After pre-compression, you have your main compression. This is actually where we're deforming and bonding those particles. Okay. There's an upper roller and a lower roller, both for pre and main. One of the rolls is going to adjust for tablet thickness, hardness, and compression force. The other roll, whether it's on the upper or the lower, is going to change your punch penetration. Where in the die do you want to make that tablet? We typically make it at the high part of the die, but you have the ability to move that down in the middle and all the way in the bottom. That's called your punch penetration. After the compression, you have your decompression stage. So what's happening in that die is you've got a die wall, you have your powder in there, the upper and lower punches are coming together to compress that material and form a compact. After compression, the upper punch is released first. So you have the belly band wall pushing against your die wall, you have your lower punch, tablet's pushing there, but you remove the load from the upper punch. So the tablet wants to expand upward. And then when you eject the tablet, if you've got a lot of internal forces in that material, as soon as you pop that tablet out, it pops off, called capping. So decompression stage is usually where we have most of our capping robustness issues. After the decompression, you have 2 more stages, and they're confused as one, but they're different. The ejection has to remove the tablet from the die wall, and it has to overcome that residual die wall force and the friction between the compact and die wall to get that tablet out. If you have a high ejection force, you want to reduce that by either doing one or two things: reducing the residual force by reducing compression. Most of the times we can't afford to do that, or adding lubricant to your formula to reduce that friction so the tablet comes out easier. That's magnesium stearate, stearic acid, proved. There's a lot of different lubricants out there, and you put some of that lubricant in to satisfy the ejection. The next step is the takeoff tablet removal. So after you eject the tablet's sitting on a lower punch face and it needs to be removed from a takeoff bar. So if you have any sticking issues or picking issues, that is different than an ejection issue. In Natoli, we focus a lot of our energy and time fixing these sticking issues in manufacturing. This is probably the #1 issue in tablet manufacturing, is sticking and picking issues. So at Natoli, we focus a lot of our energy on different steel types and coatings. There's different ways of designing your tablet and the concavity, the logos, or special engraving cuts that we use. So we spend a lot of time and energy trying to fix these sticking issues. But what we're discussing here is R&D level. So we want to identify these issues at the R&D stage so we can fix them. Because once they go to manufacturing and the product's been filed, we can't change the formula unless we go through SUPAC changes. So what we could do is fix it mechanically by changing punch head flats, steel types, different coatings, engraving cuts. So there are some techniques to fix these problems, but the best way to fix it is find it at the bench scale. So that's what we're focusing on here. So that's the rotary press process. And now what we're going to do is talk about the APAP 20, 40, 6% blend, comparing that to the direct compression and roller compaction process. Well, here's our RD30. We use a BD combo turret. You can get this in B tooling and D tooling, or like what I have is a BD combo. So I have flexibility of using B tooling or D tooling on the same turret and just change the cams out. It's a very quick process. But what we did here is we ran a tabletability profile. What is a tabletability profile? Typically, a compaction profile is we incrementally increase our compression force levels, and we measure the tablet hardness or breaking force. We can look at this at force and breaking force, but I normalize the data for megapascals pressure, which is the force divided by the cross-sectional area of the tooling. And I'm also looking at the tablet tensile strength, which is the tablet hardness, then normalized to tablet geometry. So we take into account the tablet geometry, the hardness, and we use the Feld-Newton equation to derive the tensile strength. Why do we do this instead of looking at force? Well, as we increase the mass or the size of our tablet, it's going to require more force to make that tablet. But if we take the force divided by the area, we normalize for the tablet geometry. Now we're talking in terms of pressure. So if somebody says to me, hey, I compress this tablet at 100 kilonewtons of force, immediately you're going to think it's a very high force. 100 kilonewtons is very high for tableting. But if your tablet size is, say, 3-inch diameter, 100 kilonewtons isn't a lot. So if we convert that to pressure, I know 50 megapascals of pressure for compacting tablets is a very low pressure. If you made a tablet of 50 megapascal, that's a very compressible material. If you say I took 100 megapascals to make a tablet, now you're getting more into the pharmaceutical range. 100 to 200 megapascal is where most pharmaceutical products will lie between 100 and 200 megapascal. If you're at 300 megapascals, now you're approaching like the vitamins and nutraceutical industry. And if you're above that, you're in different applications like industrial applications, catalysts, batteries, things like that. So if you tell me how much pressure you put on that tablet, right away I'm going to know if that's a low pressure, a medium, or very high pressure. But when you say force, I don't know unless I know the tablet geometry and the cross-sectional area. So same thing with tensile strength and looking at hardness. If you tell me I made a tablet at 50 kP, you might think it's a very, very strong tablet. But again, if it's a large 3-inch diameter tablet, 50 kP is not high at all. But if you convert that to tensile strength, it normalizes for tablet geometry. I know 1 to 2 megapascals of pressure for tensile makes a robust tablet. Literature will actually tell you 1.7 megapascals tensile is a good target, so your tablet's robust enough to survive shipping and handling. So we typically target between 1 and 2 megapascal for a tablet strength, independent of the size. Compare a mini tab to a tablet as large as your office room. If you use pressure, now you're comparing apples to apples. So what are we looking at here? Is 20% of the APAP formulation, and we're comparing the blue profile, which is a direct compression. It's just the materials blended together and compressed, versus the roller compacted process that Al talked about. Now you'll notice that for the direct compression blend, we reached our, let's say, 2 megapascal target tensile at about 90 megapascals of compaction pressure. That's a low pressure. Remember I said 100 to 200 megapascals where typical pharmaceutical products lie? It only requires 90 megapascals, so that's very low, but it's also a very low drug load of 20%. But if we roller compact this material, we're going to increase the flowability, but you'll notice in order to achieve that 2 megapascals of strength, we need more compaction pressure, like 130 megapascal, which is still very reasonable. But the benefits here is roller compacted blend will increase the flowability and bulk density. As Al said, we went from 0.43 grams per cc up to 0.66 grams per cc. So that's a significant improvement. That'll allow me to run the press faster and have higher output of tablets. That'll help me ensure consistent tablet weights. So in this image here, look at the tabletability. It looks like the direct compression blend is favorable over the roller compacted because of the tablet strength. But like I said, 2 megapascal for roller compacted, it's only about 130 megapascals of pressure. So that's still a very low pressure. You're not going to wear out your tooling and your tablet press. It's very doable. So let's take the next step here. Let's look at 40% drug load. So as we increase the drug load, if you remember from the series 1 that we did, increasing the drug load of APAP increases the elastic rebound. So we looked at the yield of plasticity and the yield of elasticity. Plasticity is our friend in tableting because when you have plastic deformation, it represents permanent deformation. It creates bonding and it usually results in a strong compact. Where elastic recovery usually results in a weak compact, very low hardness, very low tensile strength, capping issues, lamination issues. So when we increase our APAP drug load, we know from our compaction emulation data, it's not favorable on the tableting process. But let's look at the tabletability profile on the RD30. Tensile strength versus compaction pressure again. So with 40% drug load on the APAP, we were able to achieve our 2 megapascal at a higher pressure because we had 40% drug load. It took about over 140 megapascals of compaction pressure to achieve that 2 megapascal tensile strength. How about the roller compactor? The roller compaction process, we needed quite a bit more. We're in a 250, 260 megapascal pressure range, which is still not excessively high. It's on the higher side. Like I said, 100 to 200s, typically where pharma runs, but 240, 250 is not unheard of. Most of your tools will stand 500, 600 megapascal unless you're using some exotic shapes and you got logos, and that starts to weaken the steel, but still very doable. 60% drug load. Notice I don't even have the direct compression blend here because the flowability was not acceptable. We could not get the tablet weight consistent enough to run a rotary press, so we could not run a direct compression tabletability profile with 60% drug load. Okay, so what if you want this focus on direct compression? Well, we got to do a lot of formulation work. But what we did was we roller compacted this 60% drug load, and with roller compaction, we were able to get consistent tablet weights, and we were able to acquire this tabletability profile. Notice what we have here though. As we're increasing our compaction pressure, we're increasing in tablet strength, but it's starting to level off right around this range here, about 150 megapascals of pressure. Why isn't it increasing anymore? We've reached this maximum compactability. Eventually the tablets are going to cap. And you notice this asterisk here, that asterisk represents we had capped tablets at this pressure right here. So when the curve starts to level off here, we know we're reaching the maximum compactability and then we're in danger of lamination issues or delamination issues, capping issues, and robustness issues. So to summarize this particular tabletability profile, the 20% drug loads were acceptable for both DC and roller compaction. The 40% were acceptable for both. The 60% was not for direct compression because the flowability was not there to get us consistent weights, but roller compaction did. Now, on a side note, this is actually a very nice graph to look at. When you're in R&D and you want to know your failure points of your product, this is a great curve here to say, hey, for this particular product with roller compaction, 60% APAP, we've got acceptable tablets on this linear range, but we reached this plateau right around 140, 150 megapascal. So anything above that, we're probably going to have capped tablets. We're going to have some issues with tableting. So I know it's failure point. If I were to move this into manufacturing, I'd say we cannot compress more than, I don't know, let's say 120 megapascals to be safe. Once we get higher in the compaction pressure, we're getting close to this curve and its plateau. Now we're going to run strain rate studies because I want to see what happens if we increase our turret speed, which means we reduce our compaction time. When we reduce our compaction time with APAP, you're going to get that elastic recovery. You're going to have more issues. So now we got to do a speed test. So what we did here is we kept the compression force or compaction pressure constant. And what we want to do is run the RD30 at a slow turret RPM and collect a sample of tablets. And then increase the speed, collect a sample of tablets. Do that all the way to the maximum speed, which is close to, it's actually above 1 meter per second. So here are examples of strain rate studies. I want to know what happens to my material as I increase speed. Okay, so let's look at the direct compression. 20% APAP is the blue. Notice we start at a tensile strength about, I don't know, 1.9 megapascal, and it is dropping, and we have a slight increase here. So the 20% APAP doesn't show a significant amount of strain rate sensitivity. It doesn't drop too much. When you're roller compacted, it's very similar. I wouldn't say that roller compaction is increasing the strain rate sensitivity because they're both have about the same trend going on here. So there is some sensitivity, but it doesn't seem very drastic. So now we go to 40% APAP. As we increase the drug load, we know we increase the elastic recovery. Again, all from the compaction emulator data, looking at Heckle plots and work curves. We did increase our strain rate sensitivity. So when you increase the drug load from 20% to 40%, you'll notice there's a bigger drop in our tablet strength as we increase speed. For both the DC grade and the roller compacted blend, both of them are strain rate sensitive when you get to that 40%. At 20%, not so much. Okay, what happens at 60%? Remember, we couldn't even get the weights for the direct compression blend, but we were able to for the roller compacted blend. And you'll notice it's showing some strain rate sensitivity in the beginning here, and then it's leveling off. Okay, so the 40% showing a significant amount of strain rate sensitivity, the 60% not as much, but we did see that issue in our compactability profile where we reached its maximum compactability, then we started to see some capping issues. Okay. Now, in the compactability profile, we normalized for tablet geometry and the cross-sectional area of our tooling. So now we can compare tablets of different sizes. How do we do that for the strain rate study? Instead of looking at turret RPM, we want to normalize for that as well. I would not run my R&D machine and say, hey, I ran this at 50 RPM and I had great tablets. Now go ahead and run your big Natoli production press at 50 RPM. You should expect the same results. That's not true. You have to normalize for something called a pitch circle diameter. And that's what this is all about here. So here's the RD30. This is the turret on the RD30. And the pitch circle diameter is from a measurement center of die to 180 degrees center of die. That is your pitch circle. On the RD30, it happens to be 200 millimeters. So if you know the pitch circle diameter, you know the RPM, multiply that by pi divided by 60, you get something called tangential velocity. The velocity in millimeters per second. So now if I ran my R&D press at, I don't know, let's say 1,000 millimeters per second, which is 1 meter per second, and I got great results, now I can confidently say, transfer that into your large machine, but run that machine at 1 meter per second. The RPM will be different because the turret size is different or pitch circle diameter is different, but if you're talking in terms of velocity, millimeters per second and meters per second, that's normalizing for the turret size. Okay, I have this little chart down here where I'm looking at RPM versus the tangential velocity on the y-axis. Here's our RD30, and I'm comparing some common manufacturing presses, Fetties, Korsches. Here's the Reba Piccola, another Kors. So you can look at all the machines in your company, your sister company, or your contractors you're working with, and know what tablet presses they have, and you can establish this curve for all your machines. So if you're transferring product from one press to another, you know how to do that with some science-based information, not just using RPM. Okay, so this is the same data. Instead of looking at the RPM of the turret on the x-axis, we're looking at the tangential velocity. Now again, 1,000 millimeters per second is typically where most manufacturing presses run. Some are running at 600 to 800 millimeters per second. They're running at slow speed. But the larger your turret gets, or pit circle, the higher that velocity is going to be at a constant RPM. So here's a way of evaluating the 20%, 40%, and 60%. It looks just like the RPM strain rate sensitivity studies, except we're looking at velocity. So same trends, but instead of looking at RPM, we can now say I'm running my press at 800 millimeters per second. Here's the tensile strength I should expect. Here's my starting, and here's what I'll expect on my machine running at 800 millimeters per second. So this is very important. Another way of looking at this is something called dwell time. And dwell time's been used for, I don't know, a century, where dwell time is a function of the head flat and her tangential velocity. So the larger the head flat, the higher the dwell time. So when that punch hits the roller, that punch comes down, it's consolidating. When it hits the head flat, it's no longer moving vertically, it's being held at a constant strain, and it's moving horizontally, being held under that head flat, that constant dwell in milliseconds. And again, that's influenced by the size of your head flat and the turret velocity. So when you order your punches from the Natoli or wherever your tool manufacturer is, and you don't specify the head flat, you're going to get a standard head flat for B or D tooling, BB. But please note that there are different head flats available to you. So if you're doing these studies in R&D, or you're in manufacturing, you're having capping problems, this might sound counterintuitive to you, but most companies think when you increase your dwell time, you increase your tablet strength and robustness. That's not always the case, although it's the case for a lot of products out there, a lot of literature on it. But there are some products that actually will benefit from a lower dwell time and a smaller head flat, because that will influence the consolidation time and the time to tamp the air out and get that material consolidated and compressed. So note there are different head flats available to you. In R&D, I would run strain rate studies, and if I found out my material was strain rate sensitive, I know head flat's going to play a major role in the success in manufacturing. So here's examples of different head flats for D and B. And here's an example of these dwell times as a function of turret RPM with these different head flats. So you'll see how the dwell time's influenced by using different head flats. Okay. So this is the same strain rate sensitivity studies that we looked at in RPM, tangential velocity, but now I change the x-axis to dwell time. So if you know the dwell time of your manufacturing press, let's say it's running at 15 milliseconds, now you can say 15 milliseconds of dwell, I am making a robust tablet. Or 15 milliseconds of dwell, I'm still making a robust tablet, and so on. So you can look at RPM, but I suggest you convert it either tensile strength or dwell time. Okay. All right, one last thing I want to talk about when talking about scale up and looking at presses from one size to another is the punch vertical velocity. This is the consolidation time. This is also called the vertical velocity or the loading rate. This is a function of the compression roll diameter. So if you had a real small roller, that punch is going to hit that roll and come down real fast. If you had a real large roller, that punch hits the roll, it's going to come down at a slower velocity. It's going to have more consolidation time to get that air out. But let's say this for an example. Let's say I've got a press with a small roller, and I got a press with a large roller, but I've got the same head flat for both presses. Say it's a 9.5 millimeter. Well, on a small roll, that punch is going to hit and come down fast, a fast consolidation time, and it's going to have a dwell time that's appropriate for 9.5 millimeter head flat and the velocity. Where if I had a large roll, that consolidation time is going to be much longer, but if it's got a 9.5 millimeter head flat, the dwell time is going to be the same. So even with a small roll and big roll, if your head flat's the same and your turret velocity is the same, your dwell time's the same. But what's different is for a large roll, you'll have more consolidation time, more time to tamp the air out and consolidate those particles. So the roller size is very important. And if you take a look at new machines today, you'll notice that the pre-compression roller is the same diameter as the main compression roller. Why is that? Because pre-compression purpose is to get the air out and consolidate. Excuse me. So the larger the roller, the more effective that pre-compression is going to be. Where if you had a small roller, it's not going to be so effective for pre-compression as much as a big roller. Okay, so it's not the amount of force you put on Although if you put too much force on and you create bonding, that's an issue. But the more time you have to get that air out and consolidate the particles will benefit for pre-compression. So if you look at this graph here, this is an example, one compression event. As the punches hit the rolls, the punches are coming together and consolidating. That's what all, where's my mouse? That's what all of this time is right here. And again, that's a function of the roll diameter. And then after you reached its consolidation, you get into the dwell time. And this program is using peak to 20% on the unloading. Some programs use 10% to 10%, but the time's still the same. It's a function of the head flat and the turret tangential velocity. Then you have the relaxation time right here. This is the whole compression event. So dwell time is just a small area right here. Consolidation is a huge part of this compaction event. So the compression roll diameter and the turret velocity plays a role on the consolidation time. This is very important to us to understand that. Okay. So just a quick summary. The first series, we talked about compaction emulation. If you guys didn't get the video link, please let me know and we'll send that to you. But we talked about how to characterize material deformation properties, elastic materials versus plastic materials versus brittle fracture. What does that mean to us? And how does it help us select the proper excipients and diluents to make a robust tablet? We normalize all the data. Then we looked at the rotary press process, where we looked at different feeders. The fill cam dosing is very important to us. Talked about the pre-compression, main compression. We also talked about the ejection and takeoff are two separate stages. This is confused as one stage. If you're having a takeoff sticking issue, don't just add max stir rate and think it's gonna fix it. You're actually creating more issues for you. So if you have ejection issues, we approach it one way. If you have takeoff issues, we approach it a different way. And then we also have the strain rate sensitivity studies where we look at how our material behaves at different loading rates, different tangential velocity, different dwell times or RPM. So we normalize for all of this data. Okay, with that being said, I want to thank you for your attention and I'm going to hand it back over to Carrie.
Thank you, Robert. Today's webinar was the second of our series on tablet formulation techniques. Next week on February 16th, we will be providing our third and final webinar on wet granulation and subsequent tableting techniques. It would be great if you could fill out the feedback form provided by the QR code and let us know how you liked our combined webinar. It looks like we have a time for a few questions. I see from the chat that we have a few questions for Al and Robert.
Okay, great. Al, are you there?
Yes, I am.
Okay, there you are.
All right, Al, the first question for you is, what is the rationale for a gap setting of 1.5 millimeters?
We selected a 1.5 millimeter gap during our studies because we were trying to match the last screen size that we used in RFG number 2. So sometimes I try and match gap size versus top particle size that you're looking for in your particle size distribution of the final granule that we're getting. So that was the logic in that one. The gap is variable. You can pretty much pick anything you want, but matching the gap to the top screen size minimizes fines.
Okay, thank you, Al. And Robert, my company uses tablets per minute when it comes to the tablet press speed. Can this be used for transferring products from one press to another?
That's a good question. And actually, before I answer that, we have one correction here. Our last and final webinar is going to be on Tuesday, February 23rd, not the 16th. We actually, we changed that, but this isn't our original promotion. So again, the third one is on February 23rd, Tuesday. But to answer your question, Carrie, whoever's answering this, tablets per minute or tablets per hour, and using that to transfer product from one press to another is not the way you want to do that, because every machine or small machines, large machines have different pitch circle diameters, and that will influence the velocity and the dwell time. If you're using tablets per minute, you're not really normalizing for that tablet or that turret pitch circle diameter. So you do not want to use turret RPM. You do not want to use tablets per minute or tablets per hour. You want to use the tangential velocity of the turret. You want to use the dwell time, or if you can even use the loading rate. So I would use those parameters from going from one press to another, not tablets per minute. That's not what you want to do.
Okay, great. Thank you, Robert. Al, another question for you. What was the rationale for the compaction force used during these studies? Can this be changed?
Compaction force can definitely be changed and also optimized. What we try to do is select a single compaction force that would actually turn all three of the blends into a solid, robust flake. So typically the compaction force starts out, we increase it until we see a stable, solid flake forming. If we're too low, the material is going to fall back into its original powder form, which is what we don't want. If it's too high, there's going to be no room left for compression in Rob's tablet machines. So we try and find a happy medium, more or less, that we just compact the material enough so it forms a robust tablet, doesn't fall back into a fine, fluffy powdered material again, and leaves you good compression ability in the tablet press.
Okay, thank you. Robert, one last question I think we have time for. I have a single station tablet press. Can I run these profiles on this machine?
Oh, that's a good question. There's a lot of single station presses out there. We talked about the compaction emulator. There's also simulators. Those are technically single station presses, but they're very sophisticated machines. You can run profiles on there, but as far as a regular single station press, if you don't have instrumentation to measure that force, you really couldn't run these profiles and take a look at compaction pressure, versus your tensile strength. Another thing that I would be concerned about for strain rate studies is the single station press. The way the machine works is the upper punch comes down vertically, it comes up vertically, then the lower punch comes up vertically to eject and comes back down. Where on a rotary press process, these punches are going around a turret and you have centrifugal force going on and die filling dynamics. There's a lot more going on in a rotary press than a single station. So as far as tabletability profiles, if you have an instrumented press to measure the force data and you have a software like the AIM software from Natoli, then yes. For strain rate studies, you can get an idea if your material is strain rate sensitive by compressing at faster rates and seeing if there's a trend of the hardness or tablet strength going down. But I would recommend running strain rate studies on a rotary press, even if it's an R&D benchtop, because then you got the dynamics of powder flowing on a rotary turret with centrifugal force and so on. So yes, tabletability, I think it's fine. Strain rate, I wouldn't. I would go onto a rotary press to run strain rate studies.
Okay, thank you. So it looks like we have run out of time for more questions, but please fill out the feedback form and supply us with any additional questions you may have. Again, on behalf of Natoli Scientific and Alexanderwerk, we want to thank you for joining us today. We hope you enjoyed the presentations. Please use the QR code to fill out the feedback form and provide any additional questions. And stay safe and have a great day.
Thank you.
Thank you.